And at the same pilot facility that we've shown through various testing that we can actually vary our energy production to meet a given demand curve. Our value proposition here at Eavor is that our Everloop technology is basically all forms of those things. Not only is it clean, it's scalable. You can add investment dollars to it, and the production should hopefully scale linearly with each investment dollar. We can provide some minimum level of power. And in addition to that, we can also ramp up and down to maybe make up for some flagging energy sources as maybe the wind is blowing or the sun's not shining. So that really helps communities be certain that they're going to get the energy that they need, which I think is a huge global theme right now.
Hello and welcome to Say Hi to the Future, a podcast aimed at highlighting the human side of human ingenuity. My name is Ken Tenser, CEO of SpyderWorks. With me today is Colin Brown, Technology Development Engineer at Eavor, a geothermal technology-based energy company led by a team dedicated to creating a clean, reliable, and affordable energy future on a global scale. Like this video if you enjoy our show and subscribe to our channel. Leave us a comment with who we should interview next. Thank you for tuning in, and I hope you enjoy the show. So Colin Brown, welcome to Say Hi to the Future.
Thank you for having me. I'm really excited to be on.
So Colin, your background, at least by education, is mechanical engineering, but you seem to have been part of the energy industry for a very long time. How does that all tie together?
Yeah, so I've always had an interest in the energy industry, and primarily because growing up in Calgary, the energy industry has been like a really big part of the community here. And because of that, been a big part of my upbringing. Both my parents worked in the energy industry when I was growing up. And throughout university and in my early career, I primarily worked for some of the larger oil and gas companies in Canada here. And being from Alberta, it's kind of just what you expected to happen, really, is kind of how it happened for me anyways. So coming out of school, I actually worked for Cenovus Energy, which is one of the largest Canadian energy companies. But one really interesting thing, being based in Alberta, and because there's such a focus on the energy industry, the one thing that's been really interesting to see is how the energy landscape around us has kind of been changing with public sentiment and the shift that's been happening over the last couple of decades. And the really cool thing to see is how the energy companies here in Calgary, and I guess across Canada and the rest of the world, is how they're, with this new narrative going on, how they're pivoting and adapting to the new social and regulatory pressures. And yeah, I find that super interesting, and I'm glad to be part of that pivot as well.
So talk a little bit, you said the new narrative, and yes, I mean, we are based in Canada as well. And for listeners, yes, Calgary and Alberta has definitely been an oil-based industry or industry sector for many years. But what is the new narrative, and what are the newer forms of energy that you see as being critical?
I think the most common ones that will get talked about is the big push for wind and solar. I think those are some of the real big drivers against or behind the energy transition, primarily because nowadays they're so cheap. I believe both those sources of energy can provide power 3 cents a kilowatt hour or $30 a megawatt hour, depending on how you want to look at it. In my point of view, those two energy sources are critical to the energy transition, but I think it's also good for everyone to recognize that wind and solar aren't the only things that need to be considered for our transition to a net zero world, really. And I don't want to spoil too much or jump ahead, but that's really how Eavor fits into the picture. We aren't trying to be better than wind and solar. Really what we're trying to do is provide a technology that is a really great complement to some of the really established green energy sources. And I think together they can provide really good grid resilience in a net zero world.
You know, as we start to talk about Eavor, it's not wind, it's not solar, it's not oil and gas. What is it? What is it pioneering, if you will, or ahead of the curve on?
In a large bucket, you can consider us a geothermal energy source. And really what Eavor is trying to do is take something that's really being considered niche, geothermal energy, and make it something that is scalable and can be kind of implemented anywhere. in traditional geothermal projects, the real challenge has always been it's tough to scale. And the reason why it's so tough to scale is traditional geothermal really requires an alignment of the stars in terms of geology. It requires a really permeable aquifer as well as really hot rock as well. And because that's relatively difficult to find, traditional geothermal can only really, those projects can only be executed in a small portion, parts of the world, really.
So Colin, sorry, before you go on, paint a picture for us what geothermal energy is and what it means and where it comes from.
Yeah, geothermal energy is really taking advantage of the heat beneath our feet, really. There's a large amount of thermal energy in the earth. And really, geothermal energy is just trying to take advantage of that in an economic and a sustainable way, of course. But yeah, really, it's one of the most dependable energy sources on Earth. And geothermal projects are really just trying to take advantage of that, really.
So how do you take heat from beneath our feet, as you put it, and from the earth or below the surface of the earth as we know it, and capture that?
Like I kind of already alluded to, traditional geothermal projects require the production of really hot brine from permeable aquifers, and they take that hot brine and they can provide district heat, which is really popular in Europe. Or if it's hot enough, it can be actually converted into electricity as well. What our technology is trying to do is kind of remove the favorable geological conditions away from the equation. And because you don't have any sort of mass transfer, or because traditional geothermal depends on mass transfer through the earth or through the permeable aquifer, it's not always super dependable. What our technology really depends on is heat conduction, which is a relatively slow process. We've created a closed loop geothermal technology, often referred to as AGS, or an advanced geothermal system. But to really make it economic, you need to have a lot of surface area between your working fluid in your closed loop and the really hot rock. And so to do that, what we've essentially done is created a really large subsurface radiator, is really what it is. We drill a bunch of open hole multilateral legs between an inlet and a production well. This is essentially what we're doing. So to harvest that heat down in the subsurface, between the wells, we inject a really cold, benign working fluid. And so as that travels down the inlet well and then through all of our multilateral passes, that picks up heat from the hot rock, and that can carry the energy back to surface. And that thermal energy can be used for like a lot of things, like I said before, district heating networks, which are common in Europe. And in some of our more advanced designs, as the water comes up and has a lot of thermal energy, that can actually be converted into electricity as well by putting that hot fluid through something like an organic Rankine cycle.
You're not capturing the water, you're putting the water underground and it's being heated, if I understand it, by the planet. Mm-hmm. And then it comes back up. Now, how, and again, I'm a lay person. A lot of the listeners, I'd say most of them will be lay people. So you've put this water into the earth. It comes back up at an extreme temperature?
At relatively high temperature. It'll depend on where you are in the world, the outlet temperatures that are coming up, but can range anywhere from like 100 to 200 degrees Celsius, or maybe even higher.
And then what are you using this heated water for? How does that become energy as you're describing it?
So in a district heating network, like I've mentioned already, those really you're just providing hot water out to commercial or residential users in a community. To convert it to electricity, that thermal energy. So in a lot of traditional geothermal plants, the water will come out and can be flashed to steam, and the steam can drive a turbine, which then can generate electricity. In cases where the hot water isn't technically hot enough to be converted into steam, what you can do is actually transfer that hot water that we're producing from an Everloop, exchange it or transfer it to an organic fluid, like a hydrocarbon, say, and then you can actually flash that hydrocarbon to its vapor phase, and then that can be used to drive a turbine and produce electricity.
You're using the hot water and the steam from that hot water to drive the turbine, capture the electricity, and redistribute it.
Yeah, ours is because in our type of technology, the temperatures might not be super high. Instead of flashing the steam into a vapor phase, we can transfer the thermal energy to another working fluid that has a lower vaporization temperature. And then that can become a vapor, and that will turn a turbine, which produces mechanical energy, which can then be used to generate electrical energy.
Okay. So you talk about Europe. Is this happening there? Is this common? Is it starting to become commonly used or accepted, or is it more in a testing type of phase?
I'd say geothermal in general is more widely accepted in Europe than it is here in North America. Specifically talking about Everloops, though, our first commercial project is actually happening in southern Bavaria, where we've got the potential to drill and build up to 4 Everloops there. And that project will be providing both electricity and as well as district heat.
And what is district heat, as you're saying it, or you're calling it?
So in Europe, for the listeners, in North America, a lot of our heat, the heat that we use to heat our homes, is usually provided by a furnace, which is powered by natural gas typically, or sometimes heating oil in different parts of Canada and the US. But in Europe, some places they will get their heat from a district heating network, which essentially provides hot water to your home, and the home will, or and the hot water will go throughout the home, feed the radiators, and that's how they actually heat their homes there.
Okay, now, sorry, now I'm getting it. That's very cool. See, that. I'm glad you said that. Now I'm making the leap because again, and I've lived in Europe for a number of years, but I really wasn't thinking of it that way, because being North American centric, I'm thinking, well, the hot water, we have our heating systems in our house for our water, for our homes, whether, as you said, it's oil, natural gas, sometimes electric. So you are saying that this heat is actually, or the water is actually captured underground and pushed out to the homes to generate heat through radiators.
Yeah, essentially. And right now in Europe, some of their district heating is, the energy source is still fossil fuels. So a big push right now in the EU is to decarbonize or greenify their district heating networks. I believe there was a large grant that just came out in the EU recently that was basically focused on trying to make their district heating networks more green. So that's really good news for us here at Eavor, actually.
Why is this better? When you're saying it's more green, what are we taking away from using the heat from below us versus doing it individually as it comes into our homes?
We believe we've got the first scalable, clean, baseload and dispatchable power source. When we say that, it's just a lot of adjectives kind of all lumped together, and maybe not a lot of people know what all those mean together. So it sometimes is often helpful to kind of talk about what each of those adjectives mean in their context. So a clean energy source, we're typically referring to energy sources really that have little to no impact on the environment. And that impact can be defined based on how heavily we weight things like carbon emissions, land and water impacts like water intensity, and things like secondary impacts such as rare earth metals intensities. And like we've talked about already, people typically think of the clean energy sources as wind, solar, traditional geothermal, and maybe even nuclear and hydroelectricity, depending on how your ESG definition really. So that's kind of what a clean energy source is. Scalable. So for me, scalable in my mind is if we have the demand and we have the capital, that we can spend that money on a given technology and its energy output will scale hopefully linearly with the amount of investment dollars that we put into it. So some common examples of scalable energy sources are things like nuclear, wind, solar, fossil fuel power plants can also be considered scalable. But traditional geothermal right now isn't really scalable, only because you can only find so many really good aquifers in the world. So you can't just commit more and more investment dollars and expect more output. And then dispatchable and base load. So a base load resource is one that can provide some minimum level of power, electricity or heat, whatever it may be, that is available 24/7, 365 days of the year. And unfortunately, some of the leading green energy sources, such as wind and solar, aren't really considered base load, as their electricity production requires the sun to be shining or the wind to be blowing. And as such, because of that, they're considered intermittent energy sources. Some non-green forms of baseload power are like coal or natural gas power plants. So these are really reliable forms of electricity generation that are crucial to a functioning grid. And they're a really good complement to things like wind and solar, so they can kind of fill in the gaps or provide some minimum level of electricity or power. But an ongoing area of technology development right now is, can we make baseload power sources more environmentally friendly? And like I've already mentioned, nuclear and hydro do provide some level of baseload energy, but their green ratings can kind of change depending on the different ESG rating, which I know is a kind of a sticky topic right now. What is actually ESG or not? But we believe that our Everloop solution is truly a green form of baseload power. And through some of our pilot project at here in Alberta, which is just outside of Rocky Mountain House, we've shown through that it can predictably and reliably produce energy. And in addition to being a baseload power, our Everloop technology is also capable of ramping up and down production to basically match local demand or fill in the gaps between intermittent energy sources. So during the day, when you've got lots of solar, we can ramp back production on the Everloop. And then in the evenings where there's less sun and maybe more demand, we can actually ramp up our energy production to fill in those gaps. And at the same pilot facility that we've got, we've shown through various testing that we can actually vary our energy production to meet a given demand curve. Our value proposition here at Ever is that our Everloop technology is basically all forms of those things. Not only is it clean, it's scalable. You can add investment dollars to it, and the production should hopefully scale linearly with each investment dollar. We can provide some minimum level of power. And in addition to that, we can also ramp up and down to maybe make up for some flagging energy sources as maybe the wind is blowing or the sun's not shining. So that really helps communities be certain that they're going to get the energy that they need, which I think is a huge global theme right now.
Yeah, and so you talk about scalability. I guess what I'm trying to understand is, how close to source do you need to be, in the sense of, and again, it's a layperson's question. I'm guessing you can't drill and put in an installation in Central Park in New York City. So how do you power large masses or large cities like in New York or Toronto or Calgary or you name it? Is that viable, or is this more smaller or new build type of communities or plants, construction or whatever plants?
Yeah, that's a good question. A lot of people, when they think about geothermal, they can also think about heat pumps, which is usually something that an individual have for their home. But in Everloop, the way we envision it and the way that we're currently planning projects is more of like at a commercial scale level. A lot of, in electricity markets, for example, a lot of the power plants will be relatively remotely located, and then it's a grid that allows them to feed electricity in and then have that be distributed to end users. And so the way that we envision an Everloop facility to be constructed is the surface footprint is actually quite small, surprisingly. So it can be located near communities if it's required, but it can also be remotely located like a lot of our current power plants. And in a case where an Everloop is producing electricity, that can directly feed a grid and then make its way to end users.
So that's interesting. So if there's an existing grid, and I think you did touch on it when you said it, can supplement or support areas where there's intermittent sources like solar. So you can feed into an existing grid a certain amount of your power being generated. Is that so that you're supported? You're not necessarily only source going into a grid. Am I understanding that right?
That's right. And depending on the electricity market or the power purchase agreement or wherever the technology is located, an Everloop is theoretically capable of providing electricity on its own to a set of end users. But I think the way to real commerciality is becoming a part of this total grid solution, where the total grid is a combination of wind, solar, some of our current fossil fuel sources. But we believe that adding in an Everloop or a bunch of Everloops to a grid can actually add more value and provide additional resilience. There's a paper that we authored with some individuals from academia recently that has shown that a zero emission load following resource, something like an Everloop, can actually reduce the cost to operators by billions of dollars by just adding Everloops into this grid solution. And since I'm starting to talk about dollars, maybe it's helpful to kind of mention to the listeners that one of our biggest critiques right now that we get from others is geothermal technology and Everloops in general. Some people say it's not cost competitive. And in some cases, they would definitely be correct right now anyways. Wind and solar right now, they can provide electricity at about, I think their LCOE is about $30 a megawatt hour or 3 cents a kilowatt hour. Right now, our first ever project can provide electricity at about $130 a megawatt hour, which they're right, is not cost competitive. However, a lot of new technology always come down a learning curve as the technology progresses and develops and more people buy in. One point that I always like to make is as recently as 2009, solar had an LCOE of about $360 a megawatt hour. And since then, in 2021, that cost is now down to $36 a megawatt hour. So even though lots of people would say, oh, Everloops are too expensive right now, that's correct right now. But as we come down a learning curve, like most technologies do, we believe we have line of sight to costs in the $46 a megawatt hour range, which makes it really cost competitive. Even when we do include Everloops at a little bit higher dollars per megawatt hour than a lot of the other green energy sources like wind and solar, you still actually reduce total operator costs in the magnitudes of billions, because the alternative to an Everloop could be wind and solar with a lot of batteries. But to actually make that a reliable solution for the grid, you need to oversize your wind and your solar farm so that you can produce enough electricity when there's wind blowing and sun shining, and then store it and then dispatch it when there's demand in the evenings, let's say. So that's how our technology, even though maybe a little bit more expensive, in the big picture, when you're looking at the total grid, can actually reduce costs because we provide a type of energy that a lot of the other green energy sources can't provide.
And so where is Ever in its evolution? Is it, you're talking about heating and electrification. Is this happening today? Is it beta? Is it live? Where are you in that sort of growth mode?
That's a good question. In my personal opinion, I still feel like we're in a bit of a startup mode, growing as fast as we can. We do have, and I mentioned it already, our pilot project, which is just outside of Rocky Mountain House here in Alberta. That was completed in 2019. And that the purpose of that project was really to vet that a lot of our key technologies that comprise an Everloop do work together cohesively. And luckily, the pilot project did prove a lot of that and allowed us to move on to the next step, which is starting to work on commercial projects now. And We do have a pipeline of projects from around the world, but the two that I can speak to right now that are the most advanced are that project in southern Bavaria, the one that I mentioned earlier. That one there is a combined heat and power type of project. So we're sending out district heat to homes as well as providing electricity. That one is set to drill next year in 2023. And then once it started drilling, supposed to be finished and operable within a year.
Said again, the difference between your Everloop and a traditional geothermal. Just again, tell us the difference between Everloop and a traditional geothermal. Again, in a lay kind of narrative.
So in a traditional geothermal project, you really require a very permeable reservoir. And so by permeable, what I mean by that is there's enough pore space in the rock, connected pore space in the rock, so that a fluid can move very easily through it.
Mm-hmm.
And in addition to having a permeable reservoir, it also is required to be hot enough such that the energy that you do produce is hot enough to either typically to produce power, so electricity, but in some places like Europe, district heating doesn't require as high heats, but for electricity it does. And usually in a traditional geothermal project, you'll have a series of injection wells and a series of production wells. And so the injection wells will inject cold water, and that will permeate through the reservoir, picking up a lot of the heat from the rock, as well as sweeping some of the warmer water that's already in situ. That injected water will make its way to the production wells. It's then produced, and then that makes its way back to the power plant, where typically something like an organic Rankine cycle is used to convert that thermal energy into electricity. So that's a traditional geothermal project. I think a lot of the ones that do come to mind are probably the projects in Iceland. I know those ones get a lot of airtime. Our technology in Everloop, it's kind of still based on a similar concept where you're injecting fluid and then producing a fluid. But the main difference is ours is technically considered a closed loop technology. And what I mean by that is there's not going to be any fluid exchange between our wells and the reservoir or the rock. Between the injection and the outlet well, we have a series of multilaterals that are drilled between them and connect the inlet and the outlet well. And we have a proprietary technology where it's called rock pipe that allows us to seal those multilaterals that connect the injection and the outlet well. And that ensures that any injected fluid or working fluid that we have in our closed loop system does not permeate into the reservoir. So all of the heat that is in the rock is going to be picked up basically through conduction. So the conduction in the outer layers of the rock are going to slowly come towards our well as we start to produce the energy. The reason why we need to have so many multilaterals, though, is because heat conduction through a material like the rock is a relatively slow process compared to the convective heat transfer that we're seeing in a traditional geothermal project where there's mass exchange or fluid exchange. So because conduction is so slow, we require lots of surface area. And that's why we have in our technology so many multilaterals between a single inlet and outlet well.
Okay, and a multilateral is?
And a multilateral is a technology that's been adopted from basically oil and gas. There's a lot of oil and gas plays where you can drill multiple horizontal legs from a single vertical. That increases oil and gas production, basically by increasing surface area to the reservoir. And it's something that we've just inherited, but then repurposed for our geothermal closed loop system. A good analogy is maybe like a pitchfork, where the handle of the pitchfork is kind of like your vertical portion of the well or the injection part of the well. And then the tines would be the multilaterals basically. And really in some of our materials that we have online, it's essentially just kind of two pitchforks that come together and then connect at the toes, creating one closed loop.
Very cool. So it sounds like quite a step forward. I mean, and in the sense, and again, a layperson interviewing you here, but in understanding the efficiencies of the closed loop and the ability to work in different areas of the world than maybe traditionally done by other energy sources. Is that a fair statement, or is that what are the true benefits then between, maybe I'll put it that way, what are the true benefits from the Everloop or the closed system to a traditional geothermal?
In my point of view, or what our company believes, the major benefits of our closed loop system over a traditional geothermal system is the scalability. Because we don't necessarily depend on really favorable geological conditions, our technology allows us to harvest heat essentially anywhere in the world. So where there's demand, theoretically, we can locate an Everloop there, produce energy, and provide it to the communities. Whereas traditional geothermal projects, you can really only produce energy where there's really good aquifers, which may not necessarily line up with where there's demand.
Well, Colin, thank you so much for being on Say Hi to the Future as our time comes to a close. I think just one last question. I mean, you grew up, again, we talked about it at the top, in a very traditional energy environment, whether it's your family or your education, and here you are in a very technology forward company. How does it feel to be part of what could very well be the next generation or next wave of heating and electrifying the world?
It very exciting. Being a part of something where you get to do it for the first time, I think for me is where I derive a lot of my enjoyment from. Being in industries where a lot of the cool stuff has been done already, still interesting to learn about, but for me, being on the leading edge and being one of those people who gets to move things forward, to me, that's really where it's exciting for me.
Great. Colin, thank you again.
Thank you, Ken. Thanks for having me.
Take care.